Hello everyone, my name is Ted Pine and I'm a thermal engineer with Nitrexo. I am excited to share with you, the Space Thermal Control Workshop 2023 attendees, Nitrexo's continuing work on optimizing spacecraft thermal engineering processes with artificial intelligence. Today we will explore the exciting prospect of AI-driven automation in spacecraft thermal engineering. As it stands today, the spacecraft thermal engineer plays a critical role in designing and analyzing thermal control systems to ensure spacecraft can survive and operate in its mission environments. As spacecraft systems continue to evolve, becoming more complex and sophisticated, there is a growing demand for high performance systems, miniaturization, and multifunctional components. Its increasing complexity highlights the importance of accurate and reliable thermal modeling to ensure mission success. However, traditional thermal modeling processes often face challenges such as time-consuming manual efforts for model construction, modification, and validation, as well as difficulties in adapting to design changes and evolving mission parameters. Moreover, accurately modeling thermal behavior in extreme environments and for complex systems can be a very difficult task. Recent advances in AI and machine learning are now offering new opportunities for automating and optimizing thermal modeling processes. These advancements have the potential to reduce manual intervention, increase efficiency, and enable engineers to focus on high level problem solving. Throughout this presentation, we will discuss real world examples and best practices for integrating automated technologies into thermal engineering workflows. So without further ado, let's dive into the transformative world of AI-powered spacecraft thermal engineering. Before jumping in, I think it's useful to take a brief journey through the history of spacecraft thermal engineering tools, highlighting the key developments that have shaped the field today. In the pre-20th century, the foundations of thermal engineering were laid with the development of calculus by Newton and Leibniz in the 1600s, followed by the establishment of thermodynamics by Maxwell, Clausius, and Kelvin in the 1800s. The field continued to progress with the emergence of the statistical mechanics, pioneered by Boltzmann, Gibbs, and Planck. Moving into the mid 20th century, numerical methods for aerospace vehicles were introduced and quickly adopted by NASA for the design and analysis of spacecraft. These early tools laid the groundwork for the evolution of spacecraft thermal engineering. In the late 20th century, we see the proliferation of computer aided design and the advent of high performance computing, allowing for more complex simulations, propelling the field forward. As we entered the early 21st century, modern thermal analysis tools such as ANSYS, Thermal Desktop, and ISOTAN emerged, providing advanced capabilities and enhanced accuracy in thermal modeling. Now, in the mid 21st century, we are witnessing the integration of modern tools with digital assistants powered by artificial intelligence and machine learning. This transformative development is paving the way for a new era of efficient, automated, and intelligent spacecraft thermal engineering. Throughout this presentation, we will explore how these advancements are shaping the future of the field and how engineers can leverage these cutting edge technologies to optimize their workflows. It is well understood that, broadly speaking, spacecraft missions are growing in complexity. NASA's JPL has identified four primary categories of complexity factors. First being project technical design complexity. This refers to the inherent challenges and intricacies involved with designing cutting edge spacecraft systems, components, and instruments. Number two is project programmatic complexity. This encompasses the management and coordination aspects of a space mission, including budgeting, scheduling, and risk management. Third is the lack of resiliency. This factor highlights the potential vulnerability of a mission to unforeseen issues or failures, making it crucial to develop robust and adaptable systems. And lastly, number four is new design challenges. As spacecraft missions strive to achieve more ambitious objectives, engineers are often confronted with unprecedented design challenges, push the boundaries of technology. As mission complexity increases, so too does cost. And to mitigate these costs, there is a need for more efficient engineering processes. By streamlining and optimizing spacecraft thermal engineering workflows, we can achieve lower costs and ultimately enable more ambitious and innovative space missions. Traditional thermal modeling processes have several limitations. First being time-consuming manual efforts. Engineers must spend a significant amount of time creating, modifying, and validating thermal models to ensure accuracy and reliability. Number two, difficulty handling complex spacecraft systems. As spacecraft designs become more intricate and sophisticated, traditional thermal modeling methods can struggle to keep up. Limited adaptability. Traditional approaches often have a difficulty adapting to design changes or new requirements that arise during the development process. When constructing a thermal model, engineers must perform several manual tasks, such as defining geometry, materials, and properties of components, setting up boundary conditions, heat transfer coefficients, and radiation properties, balancing trade-offs between model complexity and computational efficiency, establishing thermocouplings and interfaces between components, revising models to incorporate new design changes or responding to a new mission requirement, correlating thermal model predictions with test results. So it's safe to say that whilst modern tools have allowed the thermal engineer to better design, predict, and understand their thermal control system, there still exists many time-consuming and laborious non-value added tasks in the workflow. Thus, the need to reduce that, reduce the time and cost spent here is significant. Recent developments in the AI and machine learning fields offer the potential to optimize our spacecraft thermal engineering processes. In the area of geometry construction, we can utilize convolutional neural networks for efficient shape recognition and generation in thermal models. For subsystem modeling, such as multi-layer insulation and heat pipes, we can employ support vector machines for accurate prediction of insulation properties or leverage physics-informed neural networks for enhanced understanding of heat transfer processes. Dimensionality reduction is another key aspect. By implementing autoencoders or other unsupervised learning techniques, we can generate comprehensive thermal models from simplified versions, streamlining the overall modeling process. Model tuning and optimization can be achieved by harnessing genetic algorithms, which can effectively correlate various parameters in thermal models. Lastly, knowledge transfer and communication play a vital role in any engineering project. Advanced language models can be employed for seamless education, knowledge transfer, and even automated report generation within an engineering team. Now, let's discuss the promising outcomes of integrating AI machine learning technologies into spacecraft thermal engineering processes. Time savings is a massive one. So, streamlining processes and automation leads to reduced time spent on manual tasks and model construction. Rapid design exploration. The time saved could be, in some cases, better utilized to explore design space and optimize spacecraft thermal performance even further. Improving knowledge transfer. Advanced language models facilitate the seamless communication, education, and documentation within the engineering team, and focusing on high level tasks. So, AI driven automation enables engineers to concentrate on strategic problem solving and decision making, ultimately increasing the productivity and innovation. By leveraging AI and machine learning technologies, we can really revolutionize the way spacecraft thermal engineering and thermal modeling processes are carried out, resulting in more efficient, accurate, and robust thermal control systems for future space missions. Take a look at one of the thermal engineering processes we are building automation tools for at Nitrexo, geometry mathematical modeling instruction through a real world example. The Copernicus CO2M mission plays a critical role in monitoring global CO2 emissions and contributes significantly to climate change mitigation efforts. The mission success depends on the reliable acquisition and transmission of crucial data related to CO2 emissions. The Ka band downlink antenna system is a key component of this mission, and maintaining precise thermal control is essential to ensure reliable data transmission. Any deviation in the thermal performance of the antenna system could lead to a reduction in signal quality or even loss of data, ultimately compromising mission objectives. complex instruments such as this, the creation of a GMM from the original step file is time-consuming and laborious. Furthermore, design changes may require the process to be repeated by a thermal engineer many times over. With parametric deletion, rules-based methods, as well as machine learning algorithms, Nitrexo is developing approaches to automate this process that we hope to share with the space community in the future. Let's now discuss the crucial steps for integrating automated technologies into thermal engineering workflows. The goal is to harness the power of AI and machine learning to enhance our capabilities, improve efficiency, and foster innovation. So let's really go through here 7 key steps for that. So the first, gradual integration of automation. So we begin by automating repetitive and time-consuming tasks and expand automation capabilities as team members become increasingly familiar with AI technology. Our second step, developing a multidisciplinary approach. Fostering collaboration among thermal engineers, AI experts, and other stakeholders is key. And we need to do this by encouraging cross-functional systems and teams and continuous learning to keep up with technology advancements. Ensuring data quality and availability. Collecting and maintaining high-quality data for training and validating AI models. Establishing standard data formats and protocols to facilitate data sharing and collaboration. Number 4, implementing feedback loops. Continuously evaluating model performance against test data or experimental results. Adjusting and refining AI models based on feedback to improve accuracy and reliability over time, whilst encouraging open communication between team members to identify areas for improvement. Balancing automation with human expertise. It's another crucial one. Recognizing the value of human judgment and experience in thermal modeling. Integrating AI-driven automation as a tool to enhance rather than replace human expertise. Number 6, establishing validation and verification protocols. Develop rigorous procedures to validate AI-generated models against established standards and benchmarks, ensuring the reliability and safety of AI-driven thermal models, particularly for safety-critical systems. And lastly, then, in number 7 here, fostering a culture of innovation. Encourage experimentation with new AI-driven techniques and methodologies. Support continuous improvement and optimization of thermal engineering workflows, emphasizing the importance of adaptability and resilience in the face of rapidly evolving technology landscapes. By following these steps, we can successfully integrate AI and machine learning into our thermal engineering workflows, unlocking the full potential of these cutting-edge technologies and driving innovation within our industry. I thank you for taking the time to listen to our presentation and really encourage that if you would like to collaborate with us, you can do so by reaching out at info@nitrexo.com. Other than that, thank you again very much for listening and enjoy the rest of the conference.